Okay, so our theme for today is model categories. So I'm hopefully going to give you a sense of what these are, what they're good for. But I want to start by kind of motivating them by just some ideas just from classical homotopy theory. So just within the world of topological spaces. Okay, so recall. So if I have a map of topological spaces, say F from X to Y, then this is a weak homotopy equivalence. If, when I take the induced map on all the homotopy groups of the space, then they're all isomorphisms. So I have these maps from pi n of x to pi n of y. So if these are all isomorphisms. Okay. So as the name suggests, this has maybe some relationship to being a homotopy equivalence where you have an inverse up to homotopy. And as the name suggests, it is strictly weaker than being a homotopy equivalence. So if you're a homotopy equivalence, then this implies that you're a weak homotopy equivalence, but not conversely. So you can have a weak homotopy equivalence that's not a homotopy equivalence. And so just a quick example, in case you haven't seen this before. So if you take this crazy space called the Warsaw Circle, so it's where you have a circle and then you have like a sine of 1 over x type curve coming in, and you map this to a point. So this is definitely not a homotopy equivalence because the space is not contractible. But it also has no interesting homotopy groups. I mean, in particular, it has no interesting pi 1 because just the crazy behavior here, you can't actually map a circle in nicely. So this, just collapsing this all down to a point, this is, so this is a weak homotopy equivalence. Both spaces have all 0 homotopy groups, but it's not a homotopy equivalence. This is not contractible. Yes?
Is there like a better invariant or different invariant that will actually measure the fact it's not contractible?
Well, what are you looking? What are you looking for? Just
detecting that thing is not.
Yeah, I don't know about like an algebraic invariant like this. I mean, just looking at homotopy equivalence would tell you that they're different, but yeah. I mean, really the upshot here is we want to say, well, this kind of space is pathological. And we want to say, well, when are these kind of weird things not going to happen, actually? And so basically what we're asking is there some nice class of spaces we can look at where this is an if and only if, where every weak homotopy equivalence actually is a homotopy equivalence. And it turns out that's true for CW complexes, and this is Whiteheads Theorem. Okay, so this says that if X and Y are CW complexes, then a weak homotopy equivalence between X and Y is actually a homotopy equivalence. Okay. But there are reasons why we don't want to throw out all other spaces. We still want to consider spaces that aren't CW complexes. But this says that, well, these spaces are nice in this regard. And one of the things that, that's really nice, say, about homotopy equivalence is, this is using this whole notion of homotopies between maps. It's an equivalence relation. We have all these nice things here, that don't necessarily hold here. So it's nice to know, okay, sometimes when you have this property, which is useful for other things, we actually have this stronger condition. Okay, so you say, well, but not every space is a CW complex. But we have, I guess, the next best thing, which is the Cw Approximation Theorem, which says that I can approximate any space by a CW complex in the following sense. So for any space Z, there exists a CW complex X together with a weak homotopy equivalence from X to Z. Now, so notice one thing. This says, first of all, that given any space, you can find a CW complex with the same homotopy groups. But it's actually stronger than that because it's not just having the same homotopy groups, but you have a map of spaces inducing the isomorphism on those homotopy groups. Okay, but again, we can't get away from the fact that in general this doesn't have a converse. This is, it's only a weak homotopy equivalence between the two. But if we only care about things up to weak homotopy equivalence, we can always replace a space with a CW complex, and then we have Whiteheads theorem. Okay, so we'll see a little bit later why that's going to be a nice thing to have. Okay. So a couple other kinds of functions between spaces that are useful. So the first is that of a Seraph vibration. Okay, so a Seraph vibration is a map, say P, from X to Y. So such that if I have any diagram, so I'm going to take A here is going to be any CW complex. And I think of crossing it with the interval and just including one end, just A cross 0. And if that fits into, if I have a commutative square like this, then being a Seraph vibration means I can always lift. I can find a map from A cross I up to X such that the two triangles commute. So with A is CW complex. Okay, how to make this sound like a sentence. So is a map P such that, sorry, I should have another word there. If I have this diagram with A is CW complex, then the lift exists. Okay, and then we have the dual notion of a cofibration. And there's different ways to define this. I'm going to define it so that it actually looks dual to our definition of Seraph vibration. So this is a map I from between spaces A and B such that, so for any space X, a lift exists in the diagram. So now I've got A to B on the left, and now I have X cross I over here, and then I just project out to X. So I have a lift there. Okay. Okay. Now this one's going to be more useful to think of a little bit differently. Intuitively, what you want to think of as a cofibration is you start with some space A, and you obtain B from A by attaching cells onto it. It's not up to some wiggling around a bit. But that's how you should think about a cofibration. We'll say a little bit more about that later. Okay, so what we would like to do, so now I'm going to go back to our weak homotopy equivalences. What we'd like to do is say, well, I want to ignore the difference between two spaces that are weakly homotopy equivalent. I just want to pretend that there's no difference between them. But a weak homotopy equivalence is definitely strictly weaker than an isomorphism, which would be a homeomorphism. We don't have an inverse. So we'd like to say, well, I want to change my category of topological spaces in some way so that these guys turn into isomorphisms. So I have some environment I can work where I really can't tell the difference between them. So we're going to call that the homotopy category. But we need to refine what that's going to be in order for it to make sense. So we want to form a category with the weak homotopy equivalences invertible. Okay, so objects are still just going to be the topological spaces. That's not going to change. And I guess secretly here you should be putting a few restrictions like that these are compactly generated Hausdorff spaces or something like this, but I'm not going to worry about that too much. Okay, but now, so we want, our initial idea is to do as little damage as we can. So our first idea is, well, so we want more isomorphisms. Okay, so we could, so our first idea is, well, let's just formally invert them. Formally invert the weak homotopy equivalences. And this, if you haven't seen this before, this is analogous to an algebra where you localize a ring and you say, well, I want to give some element of my ring an inverse that maybe didn't have it, and you throw it in, and then you know, it might generate some other things. So what we're going to do is say, okay, every time I have a weak homotopy equivalence, then we're going to just stick in an inverse to it. We're formally going to throw in another morphism that is an inverse. Well, this causes some problems, however, because I could potentially, I mean, the category of topological spaces is a large category, and large in the sense, in the technical sense. It's objects don't form a set. It's huge, and so there's an awful lot of weak homotopy equivalences. And if we throw in, you know, we not only throw these morphisms in, but then you have to compose them with everything else, so you still have a category. And it turns out you can get some big set theory problems when you do this. Well, what kind of problems would you have? Well, we're okay in a category if you have a class of objects, if they don't form a set. But we really want, if you take two objects, look at the maps between them, you really want that to still be a set. And if you just do this, that may not be true anymore. Okay? I don't want to spend a lot of time talking about how that can happen, but just know that there's set theory problems if you do this. So we want a better idea. Say, well, you know, what could we possibly, what could we do? Well, something that we like to do in topology often is to say, well, I don't really want all maps between spaces. I'm just going to take homotopy classes of maps. And that would certainly reduce how many of them that I have. Okay, so that's definitely going to help with our size issues, except we have different issues, and it comes back to this issue of not all our spaces are CW complexes, and so things aren't necessarily well behaved. So if our spaces are not CW complexes, then this homotopy category is not going to have properties that we want it to have, in that it's not going to be homotopy invariant. Well, what do I mean by that? Well, I could have two spaces, X and Y, which are, originally are weakly homotopy equivalent. I've now turned them into an isomorphism in this category where I've inverted things. But if I take homotopy classes of maps from, say, X and Y into Z, this may not be isomorphic. Well, I don't want that to be true. If I have spaces that are isomorphic in my category, then it shouldn't make a difference when I map into some other space. I should get the same thing. So this is, homotopy classes somehow aren't as well behaved as I want them to be. So what I really want here is to say, well, I really want to pretend every space is a CW complex. Okay. So I'm going to take morphisms in the homotopy category. Okay, so I'll write this as ho of top. Are homotopy classes of maps and now I'm going to hit everything with the Cw Approximation Theorem and say, well, these aren't homotopy classes of maps between the spaces, but between Cw approximations of the spaces. And now, homotopy is going to be well behaved. Okay, so now why did I introduce these fibrations and cofibrations? This seems to be an interruption in the middle of this whole discussion about homotopy equivalence versus weak homotopy equivalence. But I claim that this structure of fibrations and cofibrations are secretly making all this work. Okay. And one question we might have is, well, I'm claiming that these fibrations and cofibrations are relevant here, but, and I haven't told you why, but there's this question of, well, what is it about topological spaces here that makes this work? Why does, I can overcome all these problems and I can come up with some homotopy category of spaces where things behave. Well, maybe I want to do something similar somewhere else, in some other category, not topological spaces, or maybe in topological spaces with something other than weak homotopy equivalences. Could I formally invert those and make it work? So what properties of the category of topological spaces are we using here? And this is what's going to lead us to the definition of a model category. Okay, so hang in there. The definition's going to be a bit long, but okay. And this is all due to Quillen. Okay, so a model category. Well, first of all, it needs to be a category. It's just going to have a lot of extra structure. So it's a category, C, and it's going to have 3 distinguished classes of morphisms. I'm going to specify 3 different kinds of morphisms in there. Okay, so these names are definitely going to be taken from topology. So the first and most important class are going to be the weak equivalences. And we're going to indicate these by an arrow with a little equivalent symbol. And then we're going to have fibrations, which we're going to denote by an arrow with 2 points. And lastly, we're going to have cofibrations, and these are going to be denoted by an arrow with a hook. Now, these notations are suggestive. I mean, weak equivalences, these are things we want to think of as some kind of equivalence, but are, well, generally not isomorphisms, or we wouldn't have to go through all this. Fibrations are often surjective, not always, but in examples, or close to it. Cofibrations are usually some kind of inclusions or monomorphisms. Again, they don't have to be, but often in practice they are. So that's why the notation often looks like it does. And these classes need to have some properties. So they each need to contain all the identities. So every identity map needs to be a weak equivalence of fibration and a cofibration. And they all need to be closed under composition. So I compose 2 fibrations, I want to get another fibration. No.
Can you be 2 at a time?
Yes. Yes. In fact, I was just going to give you some terminology for that. So if you have, I'm going to use the word acyclic. Sometimes it's called trivial. They're both used in the literature. So an acyclic fibration is a fibration that's also a weak equivalence, and an acyclic cofibration is a cofibration, which is also a weak equivalence. Okay. So yeah, maps that are both fibrations and weak equivalences, or both cofibrations and weak equivalences, are going to be really important also. But generally, you'll have fibrations and cofibrations that are not weak equivalences.
Can you be a fibration and a cofibration?
Yes. Yeah. Yeah, often, I mean, in practice, maps that are both fibrations and cofibrations are often not very interesting. They're often like isomorphisms or something, but in general, yeah, there could be, there's nothing stopping you from. I mean, in fact, we know like identity maps are always all 3, and yeah. Okay, so then all this information needs to satisfy 5 axioms. Okay, so the first, so I'll call them MC1. The first is just about the category itself, and that's it needs to have all small limits and colimits. Okay, so in particular, that means these are not going to be small categories, basically ever. They're always going to be large because we need to have a lot of stuff in them. Okay, and then the remaining axioms are really more having to do with this additional structure. So the second axiom, so we know that all three of them are required to be closed under composition. So if I have two maps that I know are fibrations, I compose them, I still get a fibration. That doesn't change, but we want something a little bit stronger on the weak equivalences. So we want to say that if I have, say, maps F and G, if F and G are morphisms that are composable, so such that G composed with F exists, then if two of the maps F, G, and GF are weak equivalences, then so is the third. So this is often called the 2 out of 3 property. Okay. So notice this includes being closed under composition if it's F and G that are the ones that are weak equivalences. But it's stronger because maybe you knew that F and GF were weak equivalences, then that's going to imply that G is a weak equivalence. So, I mean, in general, you can imagine maps having properties where that's not true. But this is a property we want to hold for weak equivalences. This does not necessarily hold for the fibrations and cofibrations, just for the weak equivalences. Okay, so the third axiom is that any retract of a weak equivalence fibration or cofibration is again the same kind of map. Okay, so if you haven't seen retracts of maps before, it's very similar to retracts of objects. It's just a little more complicated. So if you have, a retract of objects, you think of something like this, where you have something like this. You compose the identity. Well, here you have maybe some x prime and some y prime and some x prime, and so this would mean that F here would be a retract of G. Okay. And then so this is for all three classes. They need to be closed under retracts. Okay. Okay, now our last two axioms are going to say more about how these classes interact with one another. And the fourth one in particular should remind you of our definition of Seraph vibration and cofibration from topological spaces. So this says that if I have any diagram, commutative square, so if I have a cofibration on the left and a fibration on the right, then I want to know, well, when do I have a lift? So a lift is going to exist if either I or P is acyclic. So it's not going to be enough just to have a cofibration on the left and a fibration on the right, but if this is a cofibration and a weak equivalence, and this is a fibration, then I'm going to have a lift. Or if this is just a cofibration, but this is a fibration and a weak equivalence, then I'm going to have a lift. Okay, and if you go back to the definition of Seraph vibration, and you look at the map on the left, where you're just including the A into A cross I mean, now, haven't maybe given you justification for why that's a cofibration, but you can see that it is a weak equivalence, a weak homotopy equivalence of spaces. You're just including it into the space crossed with an interval. So, yeah.
Is this trivially an if and only if from the definitions?
It's not an if and only. So this is just a definition. I mean, this is not, we're not working in spaces necessarily. I mean, spaces will be an example. But no, I don't, it's definitely not an if and only if statement. I mean, there's no reason why you couldn't have a lift in some other situation, but we want to guarantee a lift in these two situations. Okay, so then our last axiom is that if I take any morphism in C, so f from x to y, I can always factor it in two ways. So I can either factor it as an acyclic cofibration followed by a fibration, and I can also factor it as a cofibration followed by an acyclic fibration. Okay. So that's the data of a model category. So one more piece of terminology here. So notice by axiom MC1, since we have all limits and colimits, notice we always have an initial object and we always have a terminal object. Okay. And again, we're going to take the notation from topology and just denote the initial object by empty set symbol, even though that may not actually be what the initial object is in general. And a terminal object, which I'll just write as a point, again. Just stealing the notation from topology doesn't necessarily tell you what these guys are in a given model category. And then we say that an object X is fibrant if, well, since we have a terminal object, we know we always have it. I mean, definition of terminal object is take any other object, you always have a unique morphism to the terminal object. We say that X is fibrant if that unique map is a fibration. And it's cofibrant if the dual statement is true. So you always have a unique map from the initial object to any object. And if that morphism is a cofibration, then we say X is cofibrant.
Sorry, I got kind of lost on this last part.
Yeah.
Is this still part of axiom 5, or is this?
No, this is just more notation and terminology. Yeah. Yeah, the axioms end here. This is just more stuff. I guess technically not part of the definition. Well, I mean, I guess this is still a definition. But, yeah. Okay. Okay, yeah, so yeah, I got the whole definition up, and now immediately I have to start erasing it because it's are there any other questions before I have to start erasing it? Yeah.
So in spaces, what kind of objects are fibrant and cofibrant?
Good question. I'm just about to get there. Yeah. Okay. I want to just say a couple more things, and then I'll come back to the example. Okay, so one thing to notice essentially using this axiom for is if you say you have a category and you want to put a model structure on it, you really only, in some sense, you only get to choose two of the classes of morphisms because the third one's going to be determined. You say, well, okay, I pick what the fibrations are going to be. I pick what the weak equivalences are going to be. Essentially, your cofibrations are going to be forced to the things that have the lifting property that you need them to have. Now, doesn't guarantee you're going to get a model structure. It's not like you pick two and there's going to be something that works. But if there's something that works, it's going to be determined. There aren't any, once you've picked two of the classes, there's no choice after that. There's either something that works or it doesn't. And I guess this is also true if you, pick the fibrations and the cofibrations, the weak equivalences will end up being determined. In practice, I don't know that that's ever really used. Usually you have some weak equivalences in mind, and you try to come up with one class and then make sure that the other one exists. Yeah.
Can you give me an example of an object that isn't vibrant or that isn't cofibrant?
Well, first I need to get to an example where I tell you what the fibrations and yeah. So hold on, we'll get to examples in a moment, okay? Okay. Okay, so notice that a really nice consequence, first of all, of the existence of initial and terminal objects and axiom 5 is that any space, sorry, not in spaces yet, any object of my category, I can replace it with a weakly equivalent object that's fibrant or that's cofibrant. Well, and in fact, then I could get something that's both. So axiom MC5 says every object has well, how would I do that? Well, every object is going to have a unique map to the terminal object. Now let me factor it as an acyclic cofibration followed by a fibration. And I'm going to denote this by X upper F, to indicate, so the little upper F is going to indicate it's a fibrant replacement of X. Because what did it mean to be fibrant? Well, I needed the map to the terminal object to be a fibration. And because this is an acyclic cofibration, these guys are weakly equivalent to one another. And dually, I can also get a cofibrant replacement using the other factorization. So just take a cofibration followed by an acyclic fibration, and then I'll write that as X upper C for cofibrant replacement of C. And then if you wanted, and notice that, say, if X were, fibrant already, then you could take the fibrant replacement just to be itself. That would work. You can also iterate this, so if you got something, a fibrant replacement, and then applied this construction, you could get something that's both fibrant and cofibrant if you wanted. Okay, now what was our goal? Remember, we wanted enough structure so that we could get a nice homotopy category where we can formally invert whatever our weak equivalences are and not run into too many difficulties. We get something that's still manageable. And the claim is that all this structure of a model category is going to enable you to do that. And this is where vibrations and cofibrations, and in particular fibrant and cofibrant objects, are going to come in. So let C be a model category. Okay. Then define its homotopy category so ho of C. So we're going to say that the objects of the homotopy category are going to be just the same objects of the original C. And then I need to say what the morphisms are. So in the homotopy category, what are the morphisms between objects X and Y? Well, I'm going to, this is capital Y. I'm going to say that these are homotopy classes of maps where I take a fibrant and cofibrant replacement of both X and Y. Now, you should have a serious question at this point, which is, what on earth do you mean by this? I mean, I know what this means in topological spaces, but you just said we're working in all this abstraction. So this is a non-trivial fact that I'm not going to prove just because it would take a whole lecture, is that this notion of homotopy classes of maps is well defined between objects which are both fibrant and cofibrant. In any model category. And there, I mean, there's a lot to do there in that you have to say, well, how do we define homotopy in spaces? Right? Well, you say, well, I have a homotopy between, maps, F and G. If I can say, well, I can take X cross I, and I have this homotopy, so if I restrict to one of these, here I get F, here I get G, and, the homotopy moves between them. So you have to make sense of what does it mean to take X cross I in an arbitrary model category. And it turns out, again, non-trivial fact, everything that you have in the structure of a model category says there's a way to make sense of interval object, and you can make sense of homotopy. Now, it's only going to be an equivalence relation if X and Y are both fibrant and cofibrant. So again, just a lot of, this isn't for free. It takes work to show this, but the upshot is, okay, if we're between nice objects, things that are both fibrant, cofibrant, we can make sense of this, and then we have a nice homotopy category. It's kind of a miracle, really, that this all works out. Yeah.
So are we guaranteed some kind of uniqueness if we take two spaces X and Y and we create this sort of fibrant and cofibrant?
Good question. They're not necessarily unique. I mean, these factorizations are not necessarily unique. So fibrant cofibrant replacement is definitely not unique, but it turns out that this ends up being independent of which one you take. Yeah, it doesn't. The thing is if you take, so say you took this and then you wanted to take a cofibrant replacement of XF. Let's see. So then if you did, so like X, F, C to XF, well, okay, this was a cofibrant replacement. So this is a cofibration, this is an acyclic fibration. Well, you still have this fibration here, so this is still fibrant. You don't mess up the fact that, and the same goes if you do them in the other order. So again, you may not get the same result, but they're going to be weakly equivalent. And And again, there's something to show here that that this is independent of choices of those. Often in examples of interest, these are often functorial, these factorizations, and so there is a canonical choice. It's not necessary. So it depends on, in different, some people want to assume that they're functorial, and in practice they usually are, but you don't have to. But it turns out it doesn't change this. Okay, so now let's go back and make sure this all makes sense with our motivating example, that of topological spaces with weak homotopy equivalences, Seraph vibrations, and cofibrations. Okay, so there is a model structure on the category of topological spaces. So I got just terminology here. If you sort of have, say, a model category is a category with all this stuff. If you already have a category in mind, well, you say, well, it's a model structure if you can put all this other stuff on it. So there's a model structure on the category of topological spaces with the following. So weak equivalences are the weak homotopy equivalences. Vibrations are the Seraph vibrations. And the cofibrations are as above. Well, cofibrations are cofibrations. Let me go ahead and say, so they're as I defined them above, or they're retracts. Now that I've explained what a retract of a map is, they're retracts of maps A to B, and I said this informally earlier, of maps A to B where B is obtained from A by attaching cells. So it's certainly, so you're thinking of it as an inclusion, but not just any kind of inclusion, where you're including it in a certain way. You're including it into something with just more cells attached. And I said, well, think of it as something where you're attaching cells. This is where it's not quite right. I mean, you want that, but you also want retracts of it. Well, we need our cofibrations to be closed under retracts, so we need that. Yeah.
I guess I'm worried about A being some crazy space.
Mm-hmm.
And so, there's rules for how you attach cells in CW complexes, but
Right.
what rules do you have to follow if you're just attaching an N cell to A if A has some...
Nothing. You're just saying, well, you have a cell, and you basically just glue its boundary to A
somehow
in whatever way. Yeah, I mean, B is definitely not a CW complex. If A is something weird, then B is not going to be a CW complex.
Can you iterate attaching cells, or is it just one?
Sorry, can you?
Can you iterate attaching?
Oh yeah, you can attach lots and lots of. You can attach as many cells.
Okay, so you can just select a finite number of.
Right. Well, again, remember, cofibrations are closed under composition, so you can think of just attaching, and just keep attaching forever if you need to. Okay, so now, next question. It seems like there's a lot of importance here. What objects are fibrant? Which objects are cofibrant? So in this case, all objects are fibrant. Okay, and that might be, a good exercise. If you don't believe that, go back to the definition of Seraph vibration. Convince yourself that that's actually true. And, well, okay, let's go back to this definition of cofibration. Well, if what we're starting with, right, a cofibrant object means we want to start with initial object and obtain something by attaching cells. Well, if you're starting with nothing and you're attaching cells, you're getting a cell complex. So the CW complexes are the cofibrant objects. Okay, so what this says is that I don't really have to worry about fibrant replacements here. Everything's already fibrant, and so it just doesn't matter. But remember, what did we do when we went to the homotopy category? We said take a space, replace it with a CW complex, look at maps between those, then take homotopy classes, because homotopy classes is a well-defined, well-behaved operation on maps between CW complexes. So you can start to see, okay, we have some kind of objects that are nice. You replace objects by nice objects. Now you have homotopy classes. Take the homotopy classes. That's your homotopy category. And that's an actual category, not some huge thing that has set theory problems.
Julie, I have a question. Sorry.
Yeah.
So when you're looking at homotopy classes of maps between the Cw approximations
Uh-huh.
of these spaces, are you requiring them to be continuous or also cellular? I mean, okay, continuous, duh, but
Yeah, they always have to be.
yeah, but do they have to be cellular or just any old map?
Wait, when you do the CW approximations?
Yeah, so
No, they don't have to be. They don't have to be cellular, because what does that mean? If the space you have isn't, if your initial space is not a CW complex, if it's not built out of cells, what would it mean for a map to it to be cellular?
after you do the co-fiber replacement.
I don't think it doesn't matter, because you can always replace any map between CW complexes by a cellular map.
Okay.
So another
Sure.
theorem of the same, chapter 4 of Hatcher, somewhere it's in there. So
Okay.
okay. Okay. So the next. So before I do another example, I want to talk about, well, if we have categories, what we like to do is take functions between categories, otherwise known as functors. And so what would a functor between model categories be? Well, certainly it should be a functor on the underlying categories, but presumably we want to preserve some of this structure in a model category so that it is some kind of meaningful way to relate a model category to another one.
Julie,
Yes?
quick question.
Yeah.
Do you have any other easy example?
I'm gonna do another example in a minute.
Can you just say what it is? Or?
Simplicial sets. Yeah. Another example that I'm going to give you in the problem to think about during the problem session is chain complexes. But I'm not going to. Yeah, I'm going to give that to you as an exercise, so to think about it. So, not expecting you actually to prove it's a model category, because proving something's a model category tends to be very difficult, and I haven't given you the tools for that. But give you something to think about a little bit. Okay. So we're actually going to want something a bit more than just functors. Really, a functor between model categories is going to be a pair of functors, in fact, an adjoint pair of functors. So let me remind you, first of all, what adjoint functors are. So if I have two categories, so right now I'm just in the world of categories. So suppose C and D are categories. And I have a functor F from C to D and a functor G from D back to C. That these are adjoint. So for any object X of C and any object Y of D, then if I take the functions in C between X and G of Y, I'm going to get exactly the same thing as if I take functions in D from F of X to Y. Okay. And so we say that, so F is the left adjoint and G is the right adjoint. Okay. Is this familiar to people, or anybody?
Savagely technical question.
Yeah.
We have to make sure that that's not just an isomorphism on each pair of objects, but natural, right?
Yeah.
Okay.
Yeah. Yeah. yeah, there's definitely a specific, I mean, there's a way to go from one to the other. And yeah. Okay, so this is going to be our starting point. And so we're going, here's what our notion of functor, of function between model categories is going to be. So let C and D now be model categories. So a pair of adjoint functors, so F and G as above. Oh, and by the way, if I don't specify, I use the convention that the left adjoint is always the one on top. I mean, sometimes things come up and it's not left, right, but I always use the convention that the left one goes above the right one. So any question comes up later. That shouldn't be an issue today, but maybe later on. Okay, so adjoint functors F and G define what's called a Quillen pair. Now remember, our goal here is to preserve some sort of the structure of the model category, and so we're going to say that we want F to preserve cofibrant objects. Oh, sorry, not cofibrant objects, cofibrations. Also will preserve cofibrant objects, but and G preserves fibrations. Okay, and there's a reason. I mean, you can't interchange left and right and fibration, cofibration here. I mean, this is coming from, left adjoints preserve colimits and right adjoints preserve limits. And so if you're going to preserve cofibrations, you need to preserve the initial object and fibrations, the terminal object, and so on and so forth. So there's definitely a lack of symmetry here, but it is what it has to be. Okay, now we have a stronger notion, which is that of being a Quillen equivalence. If, so for any cofibrant object, say X of C and fibrant object Y of D, so if I take a morphism X to G of Y, so something in here, and I want to say, well, if that's a weak equivalence, then its corresponding adjoint morphism over here had also better be a weak equivalence. So this is a weak equivalence in C if and only if its adjoint map f of x to y is a weak equivalence in D. Okay, so I mean, notice, for example, like in the definition of Quillen pair, we say nothing about preserving weak equivalences. And in general, you don't. But a Quillen equivalence is giving you some kind of information about, well, ultimately it's about saying that the model categories encode the same information. Okay, now how could we possibly check if this is the right notion? Well, here's our most important test. So if I have a Quillen equivalence given by adjoint functors f and g, then the homotopy category of C is equivalent to the homotopy category of D. And this equivalence of categories is given by, well, something induced by F, and its inverse is induced by something from G. You need the notion of derived functors and such to define what this is. I'm not going to go into that. I can talk to you more about it if you want. So this says that, this is our first basic test, right? We can't hope for two model categories to be equivalent. It's not going to be the right notion of equivalences if we don't get the same homotopy category. But, this is stronger. You can have things that aren't Quillen equivalent, but have equivalent homotopy categories. There's a lot more information in a model category than just in the, you lose a lot of information going to the homotopy category. But this tells us it's somehow the right thing. Do people know what I mean by equivalence of categories? Is that, anybody want to, you've seen that before, like being shy? Okay, I'm getting nods. Well, okay, if you don't know, you want to ask later, feel free. Okay, so I think I have just enough time to talk about, so now I want to bring, so far this talk has been basically completely independent of yesterday's talk. Now I want to bring it together and say, well, what about a model category on simplicial sets? Okay, so this is our next big example. So there is a model structure on the category of simplicial sets with the following. So we really want to, now what was our goal in even developing simplicial sets? It was we wanted something combinatorial that modeled topological spaces. So we really want an eye to what kind of model structure could I put on here so that I really want it to be Quillen equivalent to spaces. So I'm going to start by saying, well, let me say a weak equivalence weak equivalence is going to be a map, say F, from K to L, such that if I take its geometric realization, then this is a weak homotopy equivalence. Well, in fact, remember the geometric realization is actually a CW complex. It's actually going to be a homotopy equivalence, but it's overkill. We don't need that to say that. Then the fibrations are going to be something that have a little bit of the same flavor of the Seraph vibrations. They're going to be functions f from K to L, such that, and I'm going to have some kind of square that I want to have a lift. And here's where these horns come in that I talked about yesterday. So if I have the inclusion of, so this is the K horn of an n simplex, I can include that into the n simplex. And if I have a square that looks like this, then this is a fibration if I can lift this. Okay. And so this has a lift, and this is for every, well, notice this doesn't really make sense for n equals 0. It would just be empty. So I don't want to include that. So it's for every n at least 1, and then for every k between 0 and n. And then the cofibrations are really nice. The cofibrations are just inclusions. So super nice to describe them.
So these vibrations are just sometimes called con vibrations, is that true? Or?
Yes, yes. Yeah, they're good. Okay.
Can you put a model structure on manifolds, on differentiable manifolds, or?
No, because they're not going to be, you can take like a limit or a co-limit of manifolds and not have them be manifolds anymore. So somehow the structure is a bit too rigid. Okay, so let's talk about fibrant cofibrant objects here. Let's start, well, if cofibrations are inclusions, well, what's the initial simplicial set going to be? Well, it's just going to be the empty one. And, well, that includes into everything. So in this case, everything is going to be cofibrant. But not all objects are going to be fibrant. So what's it going to be? What's it going to mean to be fibrant? So these are going to be something called con-complexes. And really, for now, I'm just going to just use the definition here. This is just going to be, well, I'm going to have a lift with respect to all these horns. And again, the terminal simplicial set is, again, just going to be the 1-point simplicial set. Just maybe I should write this as delta 0, which is the terminal object. So it's going to be guys that have a lift here. Tomorrow, I'll talk a little bit more about what this means and how you should think about these, because they are really important. Okay, so now I want this to be Quillen equivalent to the model structure on topological spaces. And it turns out, well, we have an adjoint pair. I didn't say yesterday that they were adjoint, but we have the geometric realization and singular functors. And I believe it's the geometric realization is the left adjoint, and then the singular functor is the right adjoint. And then, a very non-trivial, well, basically putting this model structure on simplicial sets and then proving, it kind of all goes together with proving that it's Quillen equivalent to topological spaces. It's not easy. I think the main textbooks that have it in there, it's like a 60-page, ordeal. It's a big deal. And this is that, so this adjoint pair defines a Quillen equivalence. Part of the reason this is difficult is that somehow this isn't necessarily a natural condition within simplicial sets, that you're really defining your weak equivalences by translating it over. And then, so it just makes things difficult. Okay, but this is really our justification for saying simplicial sets do model spaces. And when, some of you have said, in your talks, like, okay, in this talk by space, I mean simplicial set, this is what justifies that. Now, for some purposes, you really want one or the other. They're not completely interchangeable, but for a lot of purposes in homotopy theory, they are. And this is the theorem that justifies that. Okay. Okay, so I have just a couple more minutes. Let me just say a little bit about model structures on bisimplicial sets, something we talked about a little bit yesterday. And something I'm going to definitely want to have later this week. Okay, so if I have bisimplicial sets, which in light of this theorem I often just call simplicial spaces, but I guess I'll still call them bisimplicial sets because I called them that yesterday. So I really want these, so what should a weak equivalence be between these guys? Well, what do these look like? Well, I have just a bunch of simplicial sets with simplicial maps between them. And so often with weak equivalences, you you want sort of the most straightforward thing. I mean, sometimes you have something fancier in mind, but say, well, okay, a map between these is going to be just a level. I have these maps between simplicial sets. So let's say, well, I'd really like to call this a weak equivalence if every one of these is a weak equivalence of simplicial sets. Okay, so that's going to mean that if I take xn to yn, this is going to be a weak equivalence for every n. Yeah, but that's just the definition of, I mean, this is a function, right? I mean, I'm assuming this is not just any map from xn to yn. It's one, I mean, it's a morphism of bisimplicial sets, so assume that these are the maps that make everything. Yeah. Okay, so I said that, once you have weak equivalences in one other class, that the other class is determined. And there's two canonical choices. You could say, well, I have the weak equivalences level-wise. How about I make the fibrations level-wise? You say, well, no, I'd rather the co-fibrations be level-wise. You could choose either of those, but not at the same time. So these lead to two different model structures on bisimplicial sets. Sorry?
Is the structure any model category? You can lift the simplicial objects in the model category. Can you lift, out of model category, can I lift that structure up to the simplicial objects?
Yes. Yes, in either of the two ways that they mentioned. Okay. So you could choose the fibrations to be level-wise also, and this leads to something we call the projective model structure. But you could also choose the cofibrations to be level-wise. And again, something you might, if you don't believe this, something to play around a little bit is to check that you can't choose both to be level-wise and have the lifting properties. It just isn't going to work. And this is something called the injective model structure. And these kind of guys hold more generally. I mean, you could change, you could look at simplicial objects in something else and look, in some other model category and look at that. You could also change, here we're thinking this is a functor from delta op into simplicial sets. You could take some other small category and take functors from that into simplicial sets, and you still have the same thing. So there's a lot of flexibility here.
So if I choose one or the other, how difficult is it to determine the third?
So in these guys, it's actually not so hard to get an understanding of what they are, but you need a little bit more than, you need to know a little bit more than what I've told you today. I'm happy to talk with you more if you want to know, and then just one last fact is these are actually Quillen equivalent to each other. And that often happens they have the same weak equivalences. And something I didn't say, the homotopy category just depends on the weak equivalences. So the Quillen equivalence here is just the identity from, I guess I didn't give notation here. I'll write this as, so bisimplicial sets. This just means functors from delta op into simplicial sets. So I can just take the identity functor, but it actually matters which is which. So I need this one to be, so this is the projective one with level-wise fibrations. This is the injective one with level-wise cofibrations. The idea is here, this is still just going to have inclusions as cofibrations. This one's going to have a smaller class of cofibrations. So if I want to preserve cofibrations, this had better be the left adjoint, and this had better be the right. So it's the identity functor, but it's not a Quillen equivalence in either direction. So, yeah, okay, so, all right, I'll stop there.